Okay. What we're going to talk about in this section, and I don't know how much of it we'll get done, but it's not a very long section. You can see that there's not a huge number of slides, and you know I skip over half of them anyway. We're going to talk about extrema, and I want to tell you in English what extrema means before we go any further. Extrema is maximums and minimums, basically, high points and low points. You want to maximize your profit, maximize your revenue, minimize your cost. Those are extrema. So we're going to go straight into an applications problem and talk about, what an extrema is and why it matters. Suppose that the manufacturer of a diet soft drink is disappointed by the sales after they've aired a new series of 30-second television commercials. The research analysts think that the problem is in the timing of the commercial's message, drink sparkling light, and it either comes too early in the commercial before the viewers ever become engaged in the commercial, or it comes too late after the viewer's attention has faded, or for me, it wouldn't come at all because I've already hit the mute button and got up and left. But that is what they put advertisements on there for. So after extensive experimentation, the group decides that the percentage of the full attention a viewer devotes to a commercial is a function of time in seconds since the commercial began. And it follows a quadratic equation. And if you look at the coefficient of the square term, you realize that it's a fairly broad quadratic equation, and it's upside down because that coefficient is negative, which tells you that their attention span climbs to a point and then it drops off. And they want to hit that sweet spot at the peak of that parabola. So when is the best time to present the commercial's message to have the maximum attention from the viewers? Well, what we would do is exactly what we did in the last section. We're looking for where there is a maximum. We're looking for the top of the mountain on that parabola. So we're going to take its derivative, set its derivative equal to 0, and find out what that sweet time is. So going back to the function, we're going to take 2 times negative 3 over 20, which is going to give us negative 3 over 10, times t, plus 6. The t is going to drop out, and so is the 20, and they've only determined that this is effective for the first 30 seconds. So within the first 30 seconds, the peak is going to be when negative 0.3 t plus 6 is basically equal to 0. It's going to be greater than 0 when t is less than 20 seconds. Okay, in other words, their interest is increasing for the first 20 seconds. And at 20 seconds, guess what? Oh, I don't care. It's time to check my phone, time to go to the refrigerator, time to switch channels. But after that, they're not watching anymore.
Why did it go from 30 to negative 60 to negative 6?
Yes.
Oh, okay. Well,
They did, yeah. Okay. Yeah, they multiplied the first equation all the way through by 10 to move the decimal. It would be the same thing as if they had done what they should have done and just divided negative 6 by negative 0.3, and you get the same thing. So basically, they need to deliver their punchline within the first 20 seconds. Questions? Okay, it's less than 0 when t is greater than 20 seconds. And so the retention span, as we just said, increases for the first 20 seconds, and it decreases the last 10 seconds of that 30-second commercial. So the message should appear at about 20 seconds into the commercial, and at that time the viewer will devote f of 20, which is the percentage of his attention, which would be 80% of his attention to the commercial, instead of going and getting a refill or checking the voicemail. This maximum level of attention, that 80%, is a relative maximum. But on that particular window that they said the function was good for, on that particular window, it's the absolute maximum. There is not a lot of distinction, to me, in applications between a relative maximum and an absolute maximum, or a relative minimum and absolute minimum. Because in most of our business cases, we're going to have a restricted domain. So that it's going to be on that whole domain, it will be an absolute max or an absolute min most of the time. But it is possible, if you've got a function that has a lot of wiggles in it, that on a smaller piece of the domain, you'll have what's called a relative minimum, where it might bottom out here early on and then bottom out down here later on. So that's the distinction between relative and absolute. The absolute highest one is the higher, it's the high that's higher than any other peak, or the low that's lower than any other peak. There may be more than one max and min. So basically it says as long as this number is in the domain of the function, you have a relative, or what's called a local maximum for a small window of the function, and a relative or a local minimum. So to get the distinction between absolute and relative, all of the x values of the points for this graph has relative extrema. Okay, that's all of its peaks and all of its valleys. So at x sub 1, it has a relative maximum. It's higher than all of its neighbors. That one point is higher than the points on either side of it. And it has a relative maximum again at x sub 3. But its absolute maximum, given the fact that it continues to go down forever toward negative infinity when x gets smaller, and up toward positive infinity when x gets larger, its absolute maximum is at x sub 1, because x sub 1 is higher than x sub 3. Does that make sense? And it has a relative minimum at x sub 2. It also has a relative minimum at x sub 4, but x sub 4 is the absolute minimum. It's never going to go down any lower than that. So on the interval that we're looking at, that would be the absolute. Most of the time, we're not needing to make a distinction between relative and absolute. So that's just the same thing that I just told you. Maximum, maximum, but this one's higher than this one. So on the whole interval from wherever this is to wherever this is, that is the absolute maximum. That's just a relative maximum. And same here, this is a relative minimum, but that's an absolute minimum. And again, that's only on the interval where the function is crossing the x-axis. So we can find relative extrema relatively easily. We already know how to do that. We know how to find when the slope is equal to 0, and that tells you that you're at an extrema, either a high or a low. And you can identify all the relative maxes and mins by finding out where the slope is equal to 0. Now this function actually ends here at x sub 4, but it's still a low point for the function, so it stops. It doesn't go any lower than that or any higher than that, so that really at an endpoint, you're still either at a relative max or a relative min, as long as it doesn't continue onward. Now on this side, it doesn't stop. So there's no endpoint, so there's no other minimum to be had beyond the two that we see here. Now take into account, at this point, we do have a relative maximum, but can we take the derivative and set it equal to 0 at x sub 3? It's a sharp point, so there's no derivative there. What might happen at x sub 3 though? We might have a place where the slope, the derivative, is undefined. It is possible that it's not defined or it doesn't exist there.
So can it still be a maximum if there's no undefined, if it's undefined?
It's still a critical number, so yes, it could be.
So even if it's going towards infinity, that's still be.
In that case, no. Well, it's still a critical number, but no, you don't have a max or a min because it would go to infinity and then come from the bottom and continue upward. So it all depends on, is the function undefined there, which that function is defined at that point, so that's not the problem. Or is it just that the derivative is not defined there? And in this case, the derivative is defined there. There would be some reason, either division by 0 or taking a square root of a negative, that would cause that to happen. So the derivative gives the slope of a line tangent to the graph of the function, and to find the relative extrema, like we did in the last section, we identify all the critical numbers, and, this is important, one more criteria, and we try to find the endpoints. If we have a restricted domain like we did on that first problem, it starts at 0, it ends at 30, then you look and see what's happening at 0 and 30. Look at the endpoints. And the relative extrema may exist at a critical value. It may not. Just because you have a critical number doesn't mean you have a relative extrema. It could be a place where you can't take the derivative when you have a critical number. And this is the same caution that I gave you before. Remember that this function would have a critical value at x equals 0. But x equals 0 is not a relative maximum and it's not a relative minimum. It's simply a place where the function levels out for an instant before it continues to increase. So just because, as it says at the bottom, a critical number is a candidate for being a max or a min, it doesn't mean it has to be. It's just like running for political office. You can be a candidate, but it doesn't mean you're going to win. Okay? It's a possibility, but not a guarantee. So this is what we're going to refer to as the first derivative test. If you're trying to determine when critical values are maxes or mins, we're going to apply what's called the first derivative test. And basically the first derivative test says that you set the first derivative equal to 0, find the critical numbers, and then you look on either side of the critical number to see whether the derivative is positive, meaning the function is increasing, or negative, meaning the function is decreasing. And then take into account also that it is possible that you'll have one where you've got a critical number and it's increasing before it gets to the critical number and still increasing afterward, which means you still don't have a relative extrema. And there is actually a way to test and see if that's what's happened. So this is really a summary of the last section. It says on the right of a relative maximum, tangent lines to the functions have negative slopes going downhill. And on the left of relative maximum, they have negative slopes. So this function has a positive slope, positive slope, positive, reached a maximum, then its slope becomes negative and it becomes decreasing until it reaches a relative minimum. And then it starts to increase again, meaning its slope is positive again. I'll try to keep up with the notes because I know there's places you're trying to fill in the blanks. Does anybody need me to go back a couple of slides so you can finish in? I posted the PowerPoints in D2L also, and I think I posted them in Shobi. So you'll have those to access either place that you want to go if you need to fill in. So the definition of the first derivative test, this is what the first derivative test is, and that's math language, so I'm going to put it in English. If you find the critical number, as long as the function is continuous between two numbers, and the critical number is in between, and as long as you can take a derivative at that critical number, except possibly at C itself, which means that you can take a derivative everywhere except maybe at the critical number. Then C, and that C is the only critical number. So between point A and point B, the critical number C is the only critical number. It's a maximum if the first derivative is positive before C and negative after C. And it is a relative minimum if the function's derivative is negative before C and positive after C. It's saying the same thing that we've been looking at all night long. If you've got a maximum, slope is positive, goes to zero, slope is negative. If you've got a minimum, slope is negative, it turns into zero, goes back to being positive. And the maximum or minimum is at the critical number. So this is kind of a picture of what we've been doing. So if you've got an interval from A to B, and C is the critical number, you would have a relative maximum because your slope is positive, your first derivative is positive, and then it goes to negative because it is zero at the value C. The same thing happens even if this function isn't curved, even if it's straight lines. This slope is still positive, this slope is still negative, but C in this case, there is no derivative at C. It isn't that the derivative is equal to zero there. It doesn't exist there. The derivative does not exist there. And that's because it came to a sharp point. And then a relative minimum, because here's the critical number right in the middle. Minimum means it was negative slope and then changes to a positive slope. And even in this case, it has a negative slope that changes to a positive slope. But here again, you don't have a derivative at C, so you don't necessarily have to be able to take the derivative at the critical value. But you can still test on both sides of it to see if C is a max or a min. In this case, there's not a relative extrema because the slope goes from positive to zero and back to positive. And it would also happen if it were to go from negative to zero and back to negative. And the really hard case of that is when it hits what we're going to call an inflection point, where you'd have a vertical tangent here, and then you could take no derivative at all at C. but it still goes from positive to positive. So that's actually a chart of every possible thing that can happen for every critical value. So let's look at some examples. We want to find all the relative extrema for these functions, as well as where the function is increasing and decreasing. So we're going to start out with f of x in part A, and I'm going to work through the steps with you. Okay, so here's my function. So in applying the first derivative test, first I have to have the derivative. So 3 times 2 is 6x squared. 2 times 3 is 6x. 1 times 72 is 72, and 1 minus 1 is 0, so that disappears and that disappears. So here's my derivative. And I need to know where is that derivative equal to 0. And I notice, and I usually don't, but I notice that I can divide that by 6 and that by 6 and that by 6. So I'm going to factor out a 6. And that means then I can factor the other, as long as there's two numbers that multiply and give me 36, that will subtract and give me -1.
12.
Hmm?
6 and 72.
Oh, thank you. Yeah, that would be really tough for me to find a... I'm glad your brain's more caffeinated than mine at this time of night, Joe. So 12. Well, there's only, fortunately, so many ways to factor 12. It's either 1 times 12, 2 times 6, or 3 times 4. And if this was positive 3 and negative 4, that would give me the middle term. So it's x plus 3 and x minus 4, which means f prime of x is equal to 0 if x is equal to -3, because that would make that 0, or positive 4, because that would make this factor 0. Okay? So here's my critical numbers. -3 and positive 4. So I put those numbers on a number line, knowing that f prime of x is equal to 0 at this point. So this means the slope of my function at all three of these points should be 0. And I'm sure it's going to be 0 because both my function and my derivative are polynomials, so they don't have any place, they're undefined. So then I would plug into my derivative any number that's less than -3. And I don't want to get too happy, so I'm just going to go with -4. So that's going to be my test point. Then I'm going to test, I'm sorry, I put 0 in there and said that was where the slope is equal to 0, but that's not true. That's going to be a test point. And then I'm going to test one that's bigger than 4, so I'm going to get adventurous and choose 5. And since I don't like doing arithmetic, especially when I know my brain doesn't work right, as you can well see, I'm going to go to y equals, And I'm gonna put in my derivative, which is 6x squared minus 6x minus 72, and my y1. I'm going to check and see how my table's set up, make sure that it's set up for me to ask it for values. And then I'm going to go to the table and tell it I want it to evaluate my derivative at -4. And at 0, and at 5. So what I see happening here is that on this side, my slope is positive. So that means my function is increasing. At this point, my derivative is equal to 0. It stops increasing. And in this interval, from -3 through 0 and up to 4, it's negative. Which means my function has a negative slope. And then at 4, once again, that slope is 0. And then at 5, it becomes positive. So it's going to go back up. So this tells me that x equals -3 is a relative maximum and x equals 4 is a relative minimum. Okay? Y'all get that copied down. Take my other notes out from under here so I can see the notes and see what the other function is. We ready for the next one? Okay, here's our function. First thing we do, take the derivative. So we have 2/3 times 64x to the 2/3 minus 1 minus 4. And knowing how much y'all love fractions, and sometimes I feel this way too.
64? No, it's 6x.
Excuse me?
I don't think you said 6x.
6x and 2/3
It's on my test.
minus 4.
That's strange.
Oh, maybe I just looked at it wrong. It's like always.
Oh, no, this is the function. I'm taking the derivative.
Oh, wait, what
Just do
now?
that 60.
But you've got 64x.
Yeah, put that 6x in my notes.
Oh, sorry. Sorry. Even with a calculator, I can't get it right. 6x. Where did I get 64?
I know, but you scared me.
I'm glad you're not afraid to speak up when things don't look right. Okay, 2/3 times 6, not 64. That's bad. And I'm going to change it to a fraction just in case. And it says it's 4, so that's good. And I probably could have done that, but you know, I've been up since 6 this morning, so I'm running out of steam too. And then x, 2/3 minus 1 is -1/3. And then minus 4. And since both this and this are 4, you could do that. Okay? But since we're trying to set this equal to 0, you don't have to do that. We'll get the same answer both ways. So I'm going to set this equal to 0, which means that 4x to the -1/3 power is equal to positive 4, because you move the 4 over to the other side. And that means that x to the -1/3 power is equal to 1, which is the exact same thing you get here. That x to the -1/3 power is equal to 1. Now, in reality, there's 2 ways to do this problem. One is to go back to radicals and put it in the denominator, so 1 over the square root, or excuse me, the cube root of x is equal to 1. Or you can leave it as the power. These are both exactly the same thing, it's just the way you handle them is different. If you do this, then cross multiplying doesn't get you anywhere. How is the only way that this and this going to turn into 1? If you've got a fraction, how do you know the fraction's value is 1? Yeah, anything over itself is 1, right? So if this over this is equal to 1, doesn't that have to be whatever x is, has to be 1 too? Because if you take the cube root of 1, isn't that the only way to get 1? So that tells you that x has got to be 1. And that's one of the ways they'll show you do it in the book. But usually I don't care for doing power rule problems, but in this case, since that's kind of like counterintuitive, the way that you get rid of a power in a problem where you're trying to solve something like that, first of all, I need that power to be positive, not negative. So I need to multiply it by something positive. I need that power to turn into 1. What do I multiply -1/3 by to turn it into +1/3? What can I put out here to multiply it by? Yeah. I think I misspoke. I was trying to say that I need it to be positive. I need the power to be positive, and it needs to be 1. So yeah, I would need to use -3, because -3 times 1/3 is equal to 1. But that means I have to multiply 1 by, or raise 1 to the power of -3. Okay. This I got what I wanted, x to the first power, yay. What can I do with that? Well, it's same as 1 over 1 to the positive third power, right? What's 1 to the third power? 1. 1 over 1 is 1. So whichever way you kind of roundabout have to go about getting it, your critical value there is 1. Okay? I think that one actually kind of makes you feel like you're chasing your tail a little bit. So if we know that this is the only critical value, and it appears that it is because that's the only 0 we have, then we take the number line, as we did before. We put 1 on it. We know the slope is equal to 0 at x equals 1. We know that 0 is a good test point because it's to the left of 1. We know that 2 is a good test point because it's after 1. We go back to the formula for the derivative, and f prime of 0 is 2/3 times 6 times 0 to the negative 1/3 power minus 1 minus 4. Well, that's 0. And 0 minus 1 is negative 1 minus 4. That's negative 2/3 minus 4. And regardless of what it is, all I care about is that it's negative. I could have evaluated it on the calculator just as easily, like I did before. But the point is that it's negative. It doesn't matter what the magnitude is, it's negative. So that means at this point, my slope of my function is negative because my derivative is negative. So it means my function's coming down. Okay? Then at 2, that's 2/3 times 6 times 2 to the negative 1/3 power minus 1. I'm sorry, not minus 1, minus. I should be going back to the simplified version of the derivative. The simplified version of the derivative is 4x to the negative 1/3. This one's right, it's just not simplified. So let's see. Two to the negative 1/3 power. It's a fraction. It's a very small number. And then I need to subtract 1 from that. And when I multiply that by 4, is it going to change it into positive? Nope. So it's positive. That's all I care about. Doesn't matter what it is, it's positive. So my function's going back up. So what is x equals 1 on that graph or that function? Is it a max or a min?
Is it a positive or is it a negative? It's a negative.
Oh, I'm sorry. Yes, you're right. It is negative. I think it's probably time the teacher quit and let y'all go home. Because when you multiply it by a positive number, regardless of how positive it is, it's still negative. So then my function is still negative then, and it's going that way. Okay? So What do you think about x equals 1? It's a critical number. Is it a positive? Is it maximum or a minimum? Or neither one? It's neither one. Okay? So you still apply the test, but it's neither one, and you definitely want to check your arithmetic, especially if you're me. Okay, we'll finish this one, and then I think we've been here long enough. It's almost time to go home anyway. So last one. Oh, this one's fun. X squared e to the x. I'm just going to review all over the place for chapter 12. It's product rule, and it's got an exponential in it.
Mine says H to the third.
Yeah, mine does too. I should look a little closer. Okay. What kind of problem is this? Product rule. So this derivative is 3x squared. The derivative of e to the x is the one that's everybody's favorite because it's itself. You didn't have to do anything to it. Okay? So the first part is going to be x cubed e to the x plus 3x squared e to the x. And have mercy, we need to set that sucker equal to 0. That's not going to be much fun. Although I do notice one thing. This is one of those few times where simplifying might make your life easier. Is there a common factor? E to the x. Well, yeah. X squared. So we could take out x squared e to the x, which leaves us with just x plus 3. So if x plus 3 is equal to 0, x is equal to -3. There's one of them. X squared e to the x, how would we make that equal to 0? What if x squared was equal to 0? What would x be? What's the only thing you can square and get 0? Okay. So that would be 0 times e to the 0, which is 0 times 1, which is 0. There's one of them. Now what if x squared weren't 0? How can you turn e to the x into 0? No. Is it not ever equal to 0? What is e anyway? It's just a number like anything else, and that's just a power on it. And there's no way to put a power on any number that would make it 0. Make sense? Okay. So we have two critical numbers. Okay? So we set our number line up. We put -3 on it. We put 0 on it. We pick a number to the right of 0. I like x equals 1. Put a number to the left of it. I like x equals -1. And I like x equals -4 to be on the other side of -3. And since we've got the function, this time I am going to use the calculator because I have proven to myself and everybody else tonight that I can't do arithmetic now. So I will take x to the third power times e to the x power plus 3x squared e to the x power, and go back to the table and ask it for -4 and -1 and +1. And what I see happening here is that the derivative is negative, 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 0. And then positive, 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 0. But then it continues to be positive. Okay? So that tells me that my original function is going to come down, and then it's going to go back up. At some point, there's something going on along in here. It's going to either wiggle or something, but it's going to continue going up. It's going to be positive from there on. Okay? And we can actually prove this to ourselves. Make sure I put that in there right. Yeah, I did. I'm going to turn this one off and put the original function in and see if it actually does that now. So the original function is x cubed e to the x. And that looks like a good window. Zoom 0. Let's see what happens. Okay. Why did you choose the window you did? Oh my word. I don't think we need to go anywhere near that high. Okay, so it does. If you look at it here, it is negative slope. It's a relative minimum. Increases to 0, and at 0 it kind of does that, but it still increases. Okay? We'll talk about next time how you go about finding that funny little place that does that funny little thing. That's called an inflection point. If you have questions about your Chapter 12 review, don't let me know. I will help you as much as I can, short of just telling you the answers. I will tell you if your answer's right.